Hi, good morning. Thank you for allowing me this presentation. I will start sharing a couple of videos describing who we are, what we are doing here. It's okay?
Get started whenever you're ready.
Okay. Let me know when you can see my screen. Can you see my screen?
Yes, we can see.
Okay, so I will start with 3 videos. This video shows a virtual robot this is a virtual environment in which we have, and we have a real robot in the other table. So we did this from one country to another country. As you can see, I'm able to manipulate the robot by moving my hand on top of the virtual one, and then the real robot is tracking or following the same position. So this is the first topic that we are working on. So let me move to the next or to the previous. So in this case, we have an scenario in which the robot is grasping some memories, and it has a very high precision required here. And we are inserting the memories on the slots, you know, and let's say that you have a PC and you want to assemble the PC, you want to do this with a robot. So then what I want to highlight in these videos, let me see if I can show you in the next scenario here. So is the view that we have from the robot. So in which we have a mounted camera. As you can see in this picture, we have the camera mounted here. So this is a key for us because we want to have the calibration of this camera in the position that is related to the robot. So then we are doing this work, and let me show you the other work. This is the internal view from the robot. The perspective from the camera that I referred is this. And the other is the planning, in which the robot is moving and in a very complex scenario, and he's looking for some trajectories in order to find the best solution and find the trajectory. So this is some of the solutions that we are working on, some of the videos. Now I will start with my presentation. I hope it will make more sense when I start explaining what we did, and now you know why we did. So I will kind of jump to this. So the agenda for today, can you see me?
Yes, see you.
Yes, okay. So the agenda for today is we already explained the context. Now I will explain the problem, the current approaches that we have, and then I will go through some introduction to geometric algebra. I see already so many people introduce already geometric algebra. I will go very quickly in those terms. Also, Roman already gave an introduction to kinematics, so I will skip some foils, I hope. So let me jump directly to the problem description. As you can see here, we have in this picture this robot. So this robot has this camera mounted on the end effector of the robot. And it has here a transformation, which is you want to know the X and Y and Z position of this camera, but also the orientation of the camera. So this is the problem that we are trying to solve with our solution. And this is basically what we are facing. So the traditional methods that we use to resolve this problem is having like the chessboard that you can see there, in which a human takes with the hands and put in very different positions and orientations. So with this and with all the combinations of this, we can resolve the position of the camera and the intrinsic parameters. So it depends of the resolution of the camera. It depends of many things, the accuracy of this solution. And what we are trying to do is avoiding these situations. So we don't want to use a pattern. We don't want to even process the images in order to understand where is located this camera. And we have already the intrinsic parameters, so we just want to do the extrinsic parameters, which is the position and orientation of the camera. I should mention that this is possible because this is created for real sense cameras, Intel cameras. in which you have a gyroscope integrated and IMU sensor there. So then we take advantage of the accelerometer and the gyroscope in order to take this data. So directly, as I mentioned, I will describe a little bit geometric algebra, but not the conformal thing. As all we know, the geometric algebra involves quaternions, complex numbers, dual quaternions, and projective geometry. So this is why we love geometric algebra, right? So then we use this framework. I will kind of jump into which signature we use it. I saw like in a two-dimensional plane in which Roman used it. So in this case, we use it in a three-dimensional, but it's kind of the same idea. What we have here is the general description of geometric algebra, in which you have P and Q representing the signature of this, like how many bases maps to squares to 1 and squares to -1. So in particular, we use the G63, in which we have 6 bases here. These 6 bases that maps to 1 and 3 that maps to -1. With this, we are able to kind of expand with a lot of bases, having scalars, vectors by vectors, and the pseudo-scalars containing the quaternions, octonions, sedenions, and the projective geometry. So I will go very quickly of what we have here and why we are using the geometric algebra. So particularly, we are using the geometric algebra because we want to reduce the complexity, computationally speaking, of our algorithms to make them run faster. So in the traditional Rodriguez formula, you can create a matrix like this with a lot of multiplications and additions internally that you require, like for instance, 49 multiplications and addition used to compute this matrix and multiply it. In the other side, the quaternions do it much efficient. So, but of course, all you are expert on this area. I'm just like an engineer. So just wanted to recap. And also, when you want to multiply two matrices, it's like 130 multiplications just to create the matrix and multiply the matrix just to have two concatenated transformations versus geometric algebra, in which you have less than 30 multiplications and accumulations. So it makes much faster, and this is why we are using geometric algebra. So going directly to G63, so what we are doing here is mapping in every axis in a different way. So we have 3 bases to map this axis, x-axis and y-axis and z-axis. They are independently mapped. So in conformal geometric algebra, we map all together, right? So and here we map them independently. So as a result, here we have, as you can see, the traditional Euclidean, but also we have the quadric. So the POV of two of each one of them, but they have different bases for the infinite. So we don't have an infinite point. So we have 3 infinite points, or let's say 3 infinite vectors, let's say. So then with this, we have here kind of a coordinate frame and or vector or position of the vector. So this is the difference between the conformal traditional 4-1 and this is only this difference. Computationally speaking, we are only changing the way that we are not adding them. So we compute the squares of them, but we are not adding them. So we just put them in different rows. So after that, we decided to go further. And now we notice that these axes, these bases in the infinite on X, infinite on Y and Z, they were always axis aligned. So then we try to generalize them. And then we have now those vectors here, which they are general. So you can rotate them and you can have in general position, even the orientation of every single point. So then you have the points and the orientation of the points. So now talking about the geometric primitive. So the basic one is the ellipsoid, which is the most basic primitive that we have here. We started with the equation of the ellipsoid, and we map it into this formula in which we have the traditional representation of our quadratic point. And also with this decomposition, we have the ellipsoid equation here. So you can generate an ellipsoid by wedge product of 6 points or the vector of a simple vector that describes this entity. So if we go further, we can actually have the same radius for all of the axes, and you can simplify into the sphere. So you can see that when you put all the radius equal to between them, so you go down until you have the equation of the sphere traditionally using it in conformal geometric algebra. So this is the direct mapping. The only difference is like instead of having all the radius equal, right? So you can now take one of the radius and say, oh, this is my point at infinity. So as you can see here, I take this point and I move it to the infinity. So now I have in one axis, I have this infinite thing. So that means that you can show that an ellipsoid is in fact a cylinder, or a cylinder is in fact an ellipsoid with one of the radius is at infinity, right? It's infinity. So then if you choose another axis, it will go align it to y-axis, z-axis, or axis, depending of which point you use here that you replace the other point. So this is when you change one of the points and you send to the infinity. So when you take 2 points to the infinity, you generate a pair of planes, which is a traditional used in linear algebra too. And if you take 3 points, you generate a plane. So then you have this plane because you have 3 points at infinity and 3 points in general position in a 3-dimensional space. A summary, we can have all of them, like a elliptic paraboloid, a hyperboloids, conics, and all the geometric entities. So taking these, you can intersect the primitives and then generate the kind of conics, but they are more general because they could be not in a plane specifically. They are the intersection of every 2 quadrics. So you can actually intersect the generated quadrics with another quadric and generate the collection of paraboloids there, or the parabolas. So taking into account that you can handle with the bivectors, or the intersection of 2 quadrics, or the wedge product of 5 points. You can generate those 1-dimensional surfaces in a 3-dimensional space. They looks like a string, so and that's why I call them like, oh, those are like nice strings. When you have these, so you can generate with wedge of 5 points and these, but you generate 2 like this ellipse. But if you look from the other view, it is like rounded like this. So having said that, if you take one of the points and move it to the infinity, you will generate a parabola. And if you take 3 points to the infinity, you will generate a line. So this is kind of the way is the same to the 3-dimensional space, but it applies to the 1-dimensional space. So I'm happy that Roman already explained it, the kinematics. So all we know, this is the reflection is the basis of this. And by the combination of reflections, we can actually create the translation and the rotation. So then we have here the rotor and translator because it's the combination of 2 reflections. Saying that, we added another rotor, which is the rotor for the points at infinity. So if you create this vector here, this bivector here, so it allows you to rotate the points at infinity. So then now you could have the axis that traditionally were axis aligned. Now you can rotate also the axis at infinity, and you could generate a point at infinity in any position that you want in that traditional space. So then map it this formula to this. Once we have that, we can now differentiate between the revolution and the rotation, because now you can apply these 2 transformations, concatenated them, and you can see the point not only rotates, but also you can rotate on its own axis. So it's like it has an egocentric let's say, an egocentric coordinate framework that you can also rotate. So not only rotate the point, but also rotate its own axis. So that's why, like, for instance, in quadrics, should be like the rotation of a quadric like this or a rotation like this, right? So because you are adding the other terms, this and the other terms that traditional rotor has. Oh, sorry. So so let me go through directly to our paper. So now we have here, as you know, the kinematics chain that Roman already explained, in which we have a lot, the multiplications of all of the motors, right, in order to get the direct kinematics, the forward kinematics. That was already explained for many people here and in other presentations, so I will just skip. The differential kinematics is simply compute the derivative of this. So when we do the derivative, you can see the point appears one more time. So here, and then we can generate a very small formula here. This small formula that we can compute based on the velocities and the angles. We just do these operations and we have the final point, which is the velocity of the final end effector. So this formula is actually in another paper that I can give you the reference if you want. Using that, we basically computed the acceleration too. And to compute the acceleration is just like the second derivative, right? So then we have this formula in which this corresponds to multiplications between the axes. So, and you can see X is actually outside of the formula here also. So then we can actually understand where is the n effector by having all of the axes and also having a lot of observations. So the first thing that we do is computing or comparing or different or forward kinematics against the estimated with the mathematical equations, right? So measure and compute it, and we have high precision in terms of the errors we were able to estimate. After that, obviously, we compute the differential kinematics and compare against the one estimated with the accelerometers that we have. We notice small errors, as you can see here, very, very small errors, and they are so small, which we can actually align them with the original equation, the mathematical approach that we already have, and just make the approximations in order to understand the position of the camera. So when you have the right position of X, the two signals will be aligned perfectly. So then here we have a lot of noise because this is the measured with the accelerometer, which is a little bit noisy. Let's say, but by having all of like what we do is like we put the robot and we move the robot. So after moving the robot, it estimates these functions and we approximate it with the mathematical formula, and then we get the right parameters. So this is for the estimation of the orientation of the camera. We also did the same approach in which we are interpolating the noisy function obtained by the gyroscope. And at the end of the formula, at the end of this process, we were able to estimate the right position of the camera and the right orientation of the camera using the gyroscope and the accelerometer. Obviously, the orientation of the camera is known, so many people is doing that, right? So with the gyroscope, but we are combining all together to get also the position relative to the position of the robot. So saying that, so we don't require human intervention, we don't require a visual pattern. We could have the calibration with the camera mounted. We use a geometric algebra to do this. We use it only the information of the IMU sensors. We don't require, as I mentioned, turn on and do visual processing of the videos in the camera. So saying that, I want to thank you for your attention. I hope I am on time.
Yes, you are.
Okay.
Yep.
So I am open for questions.
Thank you, Julio.
Thank you.
Are there any questions?
I'm really curious how much of you just showed us is implemented in the embedded Movidius processor, the vector processor versus outside.
Yes. So let me show you something. You mean this one, right?
Yes.
Right. So this is the Movidius.
Right.
We mapped actually all the neural networks and some of the solutions to this. Actually, I have it here on my hand. And also the technique I am using to make this presentation, this hand detection, as you can see, is also a neural network that is running on this device. And it's also, we have the kinematic of the hand with the geometric algebras. So it's not part of the presentation, but yeah, it was kind of a plus.
Other questions? No, do we have any on the chat? Also not, then
oh wait,
thanks.
Hang on, there is one here. So, so this is from Duncan. What software did you use to render the geometric surfaces / strings for the presentation?
Oh yeah, I created my own software, my library. I never publish it, but I can share if somebody's interested. It's very limited, I should say, because I mean I didn't have the intention to share it, right? So it's like not well documented, but I can share it if somebody is interested. Internally, it has a C++ library for any geometric algebra, so you can specify any size of geometric algebra, any signature, and you can use it. This is on DirectX and also OpenGL, so I have the two versions. And yes, so you send me an email and I can reply back with the content. But I love a lot of people using like Gallop and using Clucal and other stuff, which are much better visualizations. So somebody sent me a link to a web page I saw the G63 there, and it was amazing. So they have even better graphical representations of it, I should say.
Thanks, Julio, for mentioning that.
It looks like we have one more question actually from Todd or Hamish. Let's see, hang on, let me post here.
Oh.
Well, thank you so much.
Oh.
Thank you for your attention then.
Okay. All right, Stephen.
Yeah, can I still ask a question?
Yeah, Stephen, you can ask a question.
Okay, Stephen here. So if I got that correctly, then you're basically not using any of the camera input anymore, but doesn't that imply that you'll have a drift eventually? And are you doing anything to compensate that?
Yes, actually, this is because the movements we have is like we move one by one, and then we go to home position again, right? And then we move, let's say that you move one axis, and you have, let's say that you rotate the first axis, and then you are expecting to generate a circle, right, in the general position, and you are also expecting a specific acceleration, so you know what you are expecting, right? And then all you need to do is a little bit of adjustment based on what you are getting from what you were expecting to have. And then we again go back to home position, and then we move the other axis, and we do that. So the drift is in somehow mitigated because those are different experiments. This is like when, do you remember the movie Wall-E, when he connects the camera and he plugs his own camera, and then he moves the eyes in order to detect or calibrate them? So this is very similar. So you just plug the camera and it start moving a little bit, and then it detects where is exactly located.
Okay, but that works because there are absolute values there. I mean, if all the
Yes.
sensors you use are relative, then eventually, I mean, your state will drift away from the.
Yes, exactly. Yes, it's only because that a specific configuration. Yeah, it's not in general. So we have a specific motions and a specific setup.
Okay.
Yeah, very good question.
Okay, and then we can't hear you.
Hamish?
I think you're Hamish. I think we can't hear what you're saying here. Maybe you can send it.
Cannot hear
send it
you.
in the chat. Okay. Okay, and I think looks like there are no other questions.
Do we have other questions? Yes.
Hi, Julio. It's Chris Doran here. Thanks for that talk here. It's really fascinating. In the past, when I've seen G63 and thought it looked interesting, but I've always been put off because it looks like the basic construct is very rigidly tied to your choice of X, Y, Z axes at the very start. Is this whole setup kind of equivariant? If you chose your axes differently, does it all work in exactly the same way? Or is this sort of initial choice pretty critical?
That is a very good question. So in the original, let's say, formulation of the G63, what we have is always 3 points at infinity, right? Infinite vectors that they are axis aligned. So then when you try to rotate a primitive, it get destroyed because what it does, it internally rotates the points that creates the primitive, and it generates different primitives, always axis aligned. So by doing this, you can actually have points in a different, all them in a different orientation, and then do the wedge product of them and generate the primitives, oriented primitives. So that is the main difference between the original formulation and this one. So I was trying to identify the situation. So I just, the solution was the rotation of the points at infinity, because at the end of the day, you are moving the points at infinity in that specific direction, right? So then the primitives go to that direction and generates the primitives in that shape. But if you can rotate them, if you can rotate the point at infinity, you are rotating now all the points that compose the geometric primitive. It's not only the 6 points, sorry, not only the 3 points, but also the other 3 infinity points, right? So that you create. I'm not sure if I was clear, but we could have a further conversation if you want.
Okay, thank you, Julio. Other questions? Hamish?
Okay, let's see. So given the path of the sort you showed, do I understand that you can also extract the transformations at each point along the path? That's a question from Hamish.
I'm trying to get exactly. Oh, yes, the transformation is, yes. So it's not for every single point. So we take all the trajectory in order to adjust and get the transformation. So in fact, it's just the position and the orientation, right? So what we are getting. And so we don't compute point by point. What we do is we do all the combination of all of them to generate a trajectory. And then based on the adjusted trajectory is what we get the right X position and the right orientation. So the orientation is already, I mean, on the literature appears, right? So when you have an IMU sensor that you can get the orientation, but what we are doing to get the position is just computing in what you were expecting versus what you get, and then adjust those values to align the equations, to align the graphs. It's not a single point, it's all the points.
Thank you. Other questions? If not, then thanks again, Julio.
Thank you for the invitation. It's really, really good. Thanks.